So this fraction value will be increasing, and then 1 minus that will be smaller. So the smaller number will be multiplied with lambda, and therefore the contribution, the effective reproductive number output will be per individual reproductive contribution will keep on diminishing. Does that make sense? And then basically then we are essentially trying to capture this kind of phenomena. Eventually what will happen when nt will be equal to k, what will happen? Right. It's interesting. So here, what is happening when nt is equal to k? It's very interesting thing happening. It reached k. So nt by k is 1. 1 minus 1 is 0. Nt plus 1 is again equal to 0. That means, in some sense, what is happening is not only like this, it's going up sometime, and again it is falling down because of overcomputation, and eventually it is hitting 0. So sometime in between it will reach the maximum NT value. Does that make sense? So now our updated equation is NT plus 1 equal to lambda into 1 minus NT by k into NT. We just changed this lambda by this density dependent function, such that we have some kind of diminishing contribution of lambda as population size grows, and we are saying when it reaches carrying capacity, it cannot. Basically, everything is like sustained. Basically, it just reaches its maximum capacity, and it essentially population size becomes 0 again. Okay, so now let's modify this particular piece of code using this equation. Now generate, starting from the same thing, lambda equal to 2, keep it lambda equal to 2, n0 equal to 10, that is starting from 10, generate and tell me what are the population sizes of first 10 generations, first 20 generations, and let us plot as well. Okay? Any questions? The good point. So now here, unlike the previous one, this is a 2-parameter model. So lambda is one parameter, k is another parameter. Okay, k is called carrying capacity. Okay, let us also take k equal to, let's say, 60. Okay, now we know everything. We know the value of lambda, we know the value of k, we know the initial population size, which is 10, and now we need to generate the first 20 generations population size. And particularly with the diversity, it's difficult. But some hands-on. It's a good idea to copy paste, because that will be more and more it will be useful. Okay. So we need to modify exactly over there itself. Correct? Everything else remains the same. Right? So now let us just modify based on what all information we have. So earlier code remains the same except that equation portion, which is essentially this line. This is essentially where we are implementing the growth model, right? Earlier we had a very simple growth model. Now we have this particular growth model to implement. How's it coming? Right. R value is 2, K value is 16. Number of generations 20 we are doing, right? Yeah. Very good. You have taken K as 600. Okay, fair enough. It's okay. I'm sorry. Yeah, L is essentially 2. This lambda is L. And it's so basically every time this n will be running, it will be updating the new n. So automatically you don't have to write nd plus 1 as such. N should suffice because in the next iteration this n will be here and it will do the job. If you write it in here, you have to again make sure that you change the variable and bring it over here. So this is good. Yeah. Multiplication we have to explicitly put a star so that multiplication comes to here. This is lambda you have written, but this is k. So we just sort of remove lambda and make it L. What did you do? So okay. See, this is for to the power thing, right? But here this is just multiplication. Hmm. Hmm? Done. Super. Good. Yes. Perfect. Perfect. So it's starting from there and then slowly as the generation is going and then stabilizing. Okay. Run the plotting command also. Oh, you have to update those x and y values and then plot. Right? Agree? Not happy? Okay. Tell me where it is not happy. Thank you. Sorry. Yes. So let us go simple. Okay. So we have defined. Okay. Yeah. So we can start afresh. It's a good idea to start afresh. Start afresh. Okay. So what we need to do? We need to first define the initial conditions. Initial population size equal to 0, lambda equal to 2. Here we have another parameter which is k equal to 60. And then we are doing this initialization of the two lists. Let us initialize those things also. X equal to in place and y equal to another. So these are essentially our set of initialization. Now we will be running the for loop. Okay. So let us run the for loop for I in range 20 and colon. Right. So inside that we need to do the updated. We need to update population size. So it is n. Now this is the previous model. Now our model is this. Okay. So how do we update this thing? So n equal to basically based on this equation we need to write, right? So what is lambda? L into, okay, we have to put multiplication sign which is star, otherwise quite English. Okay, and then bracket and then 1 minus NT, our NT is essentially N only, right? But a capital N. It's case sensitive. So by K, right? That's okay. Yeah, sure. Okay, and then into NT, which is N. Perfect. So you have defined the growth equation over here, correct? Okay. Now, so this is the crux of it. And then essentially for plotting and all, we have to do this basis, which is storing those these I values, the generation numbers. So you need to store the generation numbers by storing the generation number in X's and storing this N values in Y. That you do the next time. Right. So get good. So basically, what is happening? In we have defined as 10. Now then, this 10 will be taken over here, and then it will be calculating some value based on this equation and store that value in n itself. So your this n is essentially the new n. So when the loop will run the next time, this n value already been updated. So automatically it will go in. So you don't have to define anything or return anything. Okay, within the loop itself, we have to update these things because we need to update with identities and x equal to x. Just yes. So basically, you see, when we are doing inside the pod, you can see the code, right? So when we are doing it inside the pod loop, this n is continuously changing and being updated. If you define it outside, it will have a static value. It will be sticking to that thing and it will never change. So that is what is happening over here. Okay. So that's why we need to do it this thing in an iterative manner because this n will keep on updating within the loop. Right? Okay, hold on. So let us see what is happening. So here you are defining n first. I'm just reading the whole thing. Okay. So n equal to 10, n equal to 2, k equal to 16. Open the two empty containers, which is x and y. For I in range 20, n equal to n into l into 1 minus n by k. So you can multiply n twice. So I at the beginning of the n. Right? Okay. You can also, if required, you can put n by 3 inside parentheses again. I mean, it's not strictly needed, but you can potentially. Such that we do this operation first and then do the subtraction. Okay? So do that and do this. Okay? Most of it. Any issues? Okay. Here you see there is one multiplication sign after this. What is that? It's a different graph, right? Now it is better. Okay, good. Fine. Okay. So now let us run. Everybody is on the same page. Any doubt? Anything? Conceptual issues of which you are taking care? Excellent. So now let us do this whole thing. What we have done for lambda equal to 2, we have done this, correct? Now let us run the whole thing for maybe some other species which has different lambda. Lambda is essentially called intrinsic growth rate. This is also denoted as R. Okay. Again, I mean these are called intrinsic growth rate. For some other species, maybe the R value reproductive growth is little higher. Okay. Instead of 2, let us take something like 2.6. Okay, and let us see how it looks like. So just change R2 from 2 to 2.6. What does it look? Right. So you are seeing some undulation in the beginning and then eventually sort of saturating. Right. All right. Now let us change it even further. Make it 3. What just happened? Oscillations. What is this happening? What is this sorcery? Magic. So, what does it mean in terms of biology? What is this oscillations? What does it mean? In one generation, population size is going up. In another generation, population size is going down. Why is that happening, or why this can happen? Depletion of. Okay, so depletion of resources, because of which it can come down. Why it is going up in the next generation?
Resources get replenished.
So basically, here we are basically modeling with an assumption that every generation fresh, limited but fresh set of resources will be given. As a result, so that replenishment is happening. So in one generation, maybe there are a lot of individuals, so therefore a lot of competition, and therefore very few number will be surviving. So therefore population size will be very low. But because the population size is very low in that generation, in the next generation, there will be a lot, because there will be those individuals will be producing a bunch of offspring, which will be not that high, such that it will come down. So it will go up. But because they are up now, in the next generation, again it will come down, because everybody will be reproducing equally and producing like a multiplied by some number, which will be a large number of individuals, which will be unsupported by the environment. It will come down. This particular dynamics is also, it's very much prevalent in natural situations. Okay, this is essentially termed as a boom-bust dynamics. It booms and then busts in the next generation. Booms and busts. Okay. Now, let us do this little further. Instead of 3, let us go a little ahead. 3.4 or 3.5. See how it goes. All right. Go towards 4. Like, okay, don't do 4, but 3.8. Lot more fluctuations as we are increasing the R value, this lambda value, isn't it? And eventually you will see, you will reach a zone very close to very close to 4. Will reach a zone where there is almost like no pattern. It's like fluctuating randomly. All right. Is it happening all right? So this is very interesting. Okay. So now let us do a little pause and let us watch some video. Okay. On this particular phenomenon. Okay. So far, whatever we have done, it's pretty much understandable, right? We have changed the R values or reproductive number, lambda or R, whatever way you say it, and we saw the dynamics changed completely. From stable dynamics, it fluctuates, and then eventually it became like almost like no pattern. Okay, so this is a video on this phenomenon. Okay, I hope the speaker will work. Okay.
Let's say you want to model a population of rabbits. If you have X rabbits this year, how many rabbits will you have next year? Well, the simplest model I can imagine is where we just multiply by some number, the growth rate R, which could be, say, 2, and this would mean the population would double every year. And the problem with that is it means the number of rabbits would grow exponentially forever. So I can add the term 1 minus x to represent the constraints of the environment. And here I'm imagining the population x is a percentage of the theoretical maximum. So it goes from 0 to 1. And as it approaches that maximum, then this term goes to 0. And that constrains the population. So this is the logistic map. Xn plus 1 is the population next year, and Xn is the population this year. And if you graph the population next year versus the population this year, you see it is just an inverted parabola. It's the simplest equation you can make that has a negative feedback loop. The bigger the population gets over here, the smaller it'll be the following year. So let's try an example. Let's say we're dealing with a particularly active group of rabbits. So R equals 2.6. And then let's pick a starting population of 40% of the maximum, so 0.4, then times 1 minus 0.4, and we get 0.624. Okay, so the population increased in the first year. But what we're really interested in is the long-term behavior of this population. So we can put this population back into the equation. And to speed things up, you can actually type 2.6 times answer times 1 minus answer. Get 0.61. Population dropped a little. Hit it again. 0.619, 0.613, 0.617, 0.615, 0.616, 0.615. And if I keep hitting enter here, you see that the population doesn't really change. It has stabilized, which matches what we see in the wild. Populations often remain the same as long as births and deaths are balanced.
So this part we have done, right? I mean, with small lambda or r value, we have seen that population size essentially stabilized, right? So here just one thing is that this nt by k, it has taken this k to be 1 maximum. So basically it's like this fraction it is they are using. That's why instead of 1 minus nt by k, it has essentially 1 minus x. So x is in essentially like you divide nt by k through and through, and you are doing this calculation. Okay, that's the only thing. It's basically the same thing. Okay. Now we will essentially change this r value like the way you guys were doing, and it will show exactly how the population behavior changes. All right. Okay. Let us go ahead. Oops. Sorry.
Let's say you want to model a population of rabbits. If you have X rabbits this year, how many rabbits will you...
You open it in Chrome.
.6 times answer times 1 minus answer. Yep, 0.61. Population dropped a little. Hit it again. 0.619, 0.613, 0.617, 0.615, 0.616, 0.615. And if I keep hitting enter here, you see that the population doesn't really change. It has stabilized, which matches what we see in the wild. Populations often remain the same as long as births and deaths are balanced. Now, I want to make a graph of this iteration. You can see here that it's reached an equilibrium value of 0.615. Now, what would happen if I changed the initial population? I'm just going to move this slider here, and what you see is the first few years change, but the equilibrium population remains the same. So we can basically ignore the initial population. So what I'm really interested in is how does this equilibrium population vary depending on R, the growth rate? So as you can see, if I lower the growth rate, the equilibrium population decreases. That makes sense. And in fact, if R goes below 1, well then the population drops and eventually goes extinct. So what I want to do is make another graph where on the x-axis I have R, the growth rate, and on the y-axis I'm plotting the equilibrium population, the population you get after many generations.
Is the graph clear? So basically here, so this is what is the time series, what you have plotted, right? The time on the x-axis, population size on the y-axis. Here it is being plotted in a different way. Growth rate, that is the R or the lambda what you are using, that is being plotted on the x-axis. For a particular lambda or R, will eventually the population will go to equilibrium or oscillating into two values or something like that you guys have seen. So that equilibrium population size will be plotted on the y-axis. Okay? So slightly different but understandable, right? So here the finally whatever is the long-term behavior that is being plotted over there. Okay? So let us go from there.
Okay, for low values of R, we see the populations always go extinct, so the equilibrium value is 0. But once R hits 1, the population stabilizes onto a constant value. And the higher R is, the higher the equilibrium population. So far, so good. But now comes the weird part. Once R passes 3, the graph splits in 2. Why? What's happened? Well, no matter how many times you iterate the equation, it never settles onto a single constant value. Instead, it oscillates back and forth between two values. One year the population is higher, the next year lower, and then the cycle repeats. The cyclic nature of populations is observed in nature too. One year there might be more rabbits, and then fewer the next year, and more again the year after. As R continues to increase, the fork spreads apart, and then each one splits again. Now, instead of oscillating back and forth between two values, populations go through a 4-year cycle before repeating. Since the length of the cycle or period has doubled, these are known as period doubling bifurcations. And as R increases further, there are more period doubling bifurcations. They come faster and faster, leading to cycles of 8, 16, 32, 64, and then at R equals 3.57, chaos. The population never settles down at all. It bounces around as if at random. In fact, this equation provided one of the first methods of generating random numbers on computers. It was a way to get something unpredictable from a deterministic machine. There is no pattern here, no repeat. Of course, if you did know the exact initial conditions, you could calculate the values exactly. So they are considered only pseudo-random numbers. Now you might expect the equation to be chaotic from here on out. But as R increases, order returns. There are these windows of stable periodic behavior amid the chaos. For example, at R equals 3.83, there is a stable cycle with a period of 3 years. And as R continues to increase, it splits into 6, 12, 24, and so on before returning to chaos. In fact, this one equation contains periods of every length. 37, 51, 1052, whatever you like if you just have the right value of R. Looking at this bifurcation diagram, you may notice that it looks like a fractal. The large-scale features look to be repeated on smaller and smaller scales. And sure enough, if you zoom in, you see that it is, in fact, a fractal.
Right. So this is actually part of a bigger video, which we can potentially share the link and you can just watch. This is like fascinating. But isn't it interesting? So we can actually draw this diagram, or rather, you can draw this diagram. Okay. So what we have to do now? The new job is, instead of this graph, we are now interested in drawing a graph where this axis is essentially our R or this lambda value, okay, which we are changing, and y-axis is your equilibrium population size. What is equilibrium population size?
After 100.
So equilibrium population size is essentially population size when where it will reach eventually. What is this eventually? This is. So by eventually we essentially mean, in this doable way, we run it for a long time, ignore the initial ones, and only take the last few generations. So that we are considering like eventually. Let us run for 500 generations, let's say. and then let's take only the last 100 generations population size. If it had to stabilize by the initial 400 generations, we are assuming that it would have already set out, already have reached there. So when we take the last 100, we will get the equilibrium population size. If it is supposed to do a 2-point cycle oscillations, then after this 400 generations, whatever it is, then last 100 generation will give us the exact equilibrium population size, which is oscillating. Okay, so basically we need to capture that. Okay, so now, so the revised job to achieve that, what we have to do is that, so everybody have plugged in this particular equation over here, okay, and gotten the equations. So basically, this is called logistic map or logistic equation. The earlier, this one is essentially exponential growth equation, which essentially breaks down beyond a point. So logistic one is little more realistic. So in logistic equation, what we want to run it for very, very long time, and then want to take only the last 100. Okay? Okay. So first, let me just ask you to run it for, let's say, 500 generation. Okay? Run it for 500 generation and store all these n values inside this y where you are storing, right? Okay? Okay? And after this, let us not plot immediately now. Forget about plotting now. Let us print. Okay, if we print y, it will print a lot of numbers. So let us not do that. Just to see whether we stored all 500 elements, 500 population sizes or not. Let us print the length of y. It should show us 500 if everything is stored properly. Okay, does that make sense? Okay, let us do that first. So we are essentially doing this. So for a particular r value you can keep r or lambda or L, whatever you are calling it. Keep it at any particular value. It doesn't really matter. I want all the 500 numbers inside y. Okay. Well, if you want, you can print y also, just that it will be a long list of numbers.